Welcome back to Allen High School. We're looking at models of atomic theory, and we're moving finally into the types of diagrams and representations we use to help us understand the electronic structure around a nucleus. And that's critical because structure determines function. So if we can understand the structure, it helps us understand the function, how that atom bonds, what are its properties. So it's a really important tool. Now, this is going to seem a little fuzzy at first, but I'm going to ask you to bear with me. Once I lay some groundwork, I think you're going to get this. It's not one of those tough things to understand. It's just going to seem a little funky at first because it's so abstract. So just bear with me, and I'm going to help you in class to make sure we tie this all together. There's a few types of diagrams. The first two that we're going to talk about, are orbital diagrams. What I like about orbital diagrams is they provide a lot of information because they clearly and distinctly show all four quantum numbers. That said, they can get a little annoying to draw, as you'll see. And so we want to streamline that. But bear in mind that each time we streamline a model, we're missing a little piece of information. That may be okay. You want to use the model that provides the information to help you predict the properties and understand the function. So when we streamline an orbital diagram, we get an electron configuration. It's a little bit shorter way, and we're going to find there's a shorthand electron configuration, but again, you miss a little information. So that's kind of what we're building up to. Now to do this, we need to get some terminology and some rules. They're not rules that the electron has to obey. They're rules that you need to understand because these rules describe the electron behavior the best. Okay, we can't tell electrons what to do. They do what they do around a nucleus. We're just trying to understand it and describe it. Now, remember our quantum number, our energy level, N, tells us energy and distance. Now, what's nice is that the distance relationship with N stays true. If you increase N, you increase the distance. Unfortunately, that's not true for energy. It'd be nice if they went 1, 2, 3, 4 order, but they don't. Electrons just don't go in that order. Remember, they're trying to maximize attractions and minimize repulsions. And in order to do that, sometimes the energy gets a little mixed up. Now, I'm going to show you how to do that. You're just going to have to trust me. But what's beautiful is that the periodic table gives us the perfect arrangement for filling these electrons. So that periodic table is your best tool. All right? So that's where we're headed. Now, there's a couple of dead guys, and then they named another rule just after the German for that. And let's get into those names. I'm going to come back up to this in just a minute. The Aufbau, that's German for build up, says electrons are placed in orbitals of lowest energy first. What electrons want to do is minimize their potential energy. So they go into the lowest energy available that doesn't cause too much repulsion. Right? That's, kind of the, people tend to want to be in the back row at, sometimes churches or in meetings. And so there's only so many people who can fit in the back row. So people start filling in the back row, and then they have to move forward because they can't sit in each other's lap. So electrons go as low as they can until they're just forced to go into a higher energy. That gives us this principle. The highest energy electrons, therefore, are the electrons that are in the last sublevel that you were filling in your model. Okay? Now, the outermost electrons, because energy stays true with N, our outermost electrons are the highest N energy. In fact, we're going to find the highest S and P are critical because those outer S and P are in fact, they're given a name. They're called, whoops, that's an E. Oh, Dina. They're called valence electrons. So your outermost electrons are the highest energy. Your highest energy electrons are the last sublevel filling. Okay? That's Aufbau. The next one is named after Pauli, a dead guy, and this is key. This is what Pauli says. Pauli says no two electrons can have the same 4 quantum numbers. That's like saying that no two people can be standing in the exact same space at the same time, right? We can't superimpose on one another. So what that means practically, so this is the critical real definition. We now know that an orbital can hold 2 electrons. Well, in order to make sure that all 4 aren't the same, they might have n the same, they might have l the same, they might have m sub l the same, but if we put them into an orbital with spin up and spin down, then that means that m sub s would be different. So that's how we accommodate the Pauli exclusion principle, by putting opposite spins in an orbital. And we always put the plus 1/2 spin in first because it's a little bit lower in energy. Okay? So it's kind of like if 2 guys are forced to share a bed. The first guy comes into the bed. Let's say there's no way these guys can sleep on the floor. The first person's going to come and put their head at the top of the bed. The second person will come in and sleep this way, so at least their heads aren't up against one another. All right? So that's kind of a silly thing, but it's what a lot of guys tend to do. And you guys understand that. Girls, we don't care. We'll tend to share beds so we can stay up and giggle all night. All right, Hund's rule. When filling a sublevel, this is one of the last ones, when filling a sublevel, so I'm just going to take one. I'm going to take the p sublevel. The p sublevel has 3 orbitals, so we have 3 m sub l's. All right, and what Hund's rule says is you fill each separately. I don't know what this means. It's not worded well. You fill them until each has 1 electron, and then you pair them up. So you fill 1, 2, 3, and then you'd come back and fill 4, 5, 6, because that minimizes repulsion. Okay? It's like the guys, right? If they're forced to go into beds and there's 3 beds, they're going to not go into the same bed at the same time because they want to minimize those repulsive forces. Now, want to introduce ions, and then we're going to build models of all this. We're going to tie it all together when we do examples. Now, most metals will gain electrons to become cations. And the goal is to get near the nearest noble gas. Noble gases are stable. They're inert. They are non-reactive. Those are all terms. You really need to understand that. So noble gases have maximized the attraction to the nucleus and minimized repulsions between electrons. So that's our goal, is to get to the nearest noble gas with 8 outer s and p electrons. Remember, we called those valence electrons. Okay? Now, a way to remember that the word cation is for the positive ions is a little mnemonic device, Ca positive. Do you notice that T kind of looks like a plus sign? Ion. Okay? Now, nonmetals will gain, oh, Dina, erase. Most metals, I hope some of you caught that and said, oh my gosh, what is this teacher telling us? She's giving us wrong information. Most metals are losers. Non-metals are winners. They gain. So make sure you fix that. So fix. All right? Non-metals will gain electrons to become anions. A negative ion, again, towards that nearest noble gas. All right? So if you want to kind of picture that, it sometimes helps to picture a number line, which I should have done. Oh, Dina. Okay? So if it's negative, that's a gain of those negative electrons. And if it's a positive ion, it's a loss of those electrons. Okay? So, sorry about that. Alrighty then, let's move on. Let's erase. Move on. Now, we're almost ready to build up our model then. Here we go. Let me do the summary table and then we'll move on. I'll move on to the next video. So, Group 1, their electron configuration, we put N first, then we put L, and then we put the number of electrons. And we're going to just be doing the valence or the outer s and p electrons. Group 2 ends in NS2. So it could be 1s2, 2s2, 3s2, 4s2, and so forth. Group 13 ends in NS2, NP1. Okay, so group 1 has 1, group 2 has 2, group 13 has 3 valence electrons. Now let's look at group 15. Group 14 would have been NS2, NP2. We're not going to look at some of those. I wish we would have, so make sure you write that on the bottom for completeness. Group 15 nonmetals are NS2, NP3. They have 5. Notice group 13 has 3. Group 15 has 5. Group 16 is NS2, NP4. It has 6 valence electrons. 16 has 6. And hopefully you've caught the pattern. 17 has 7. Okay. Now, we're going to talk about the metals in group 15, 16, and 17, but we're going to talk about them later. All right, we're just talking about simplest ions right now. All right, remember they lost 1 electron, lost 2 electrons, lost 3 electrons. That makes it a +1 cation, a +2 cation, a +3 cation. And remember that cations are smaller than the original ion. Okay, if I forgot to do that in the notes, the radius of the atom is greater than the radius of the cation because you're losing electrons. All right, they're closer to the nucleus. Okay, make sure we clarify that in case I missed that on that page. All right, nonmetals in group 15. Now, nonmetals, I want to focus on that. Remember, they're after 8 to get to the nearest noble gas. So this time they're going to gain 3, gain 2, gain 1 electron, -3 anion, -2 anion, -1 anion. And remember, we're talking about the nonmetals in those groups. Okay, and with anions, because you add more electrons, you have more repulsion, they push each other out, the radius of an anion is greater than the radius of an atom. Okay, that gives us some good background information. So until our next video, this is signing off.